Hi everyone, we are back and let's get to Pset 3 solutions. So let's just look at a couple of these defects. Let's take the dimensionality. So vacancy 0D, interstitial 0D, or self-interstitial, impurity interstitial, all these are 0. This is 1D, this is 2D. A void would be a 3D, and this would be a 0D defect. Now, Frankel pair and Schottky pairs must occur when I have an ionic crystal. So for example, oops, let me erase that. When I have something like NaCl lattice. So for that to occur, I need a lattice with two different lattice types, or two different atom types and two different sizes. So that's clearly not going on here. So we're dealing with some type of metallic or covalent material. So I'm not going to have any of these Frankel or Schottky defects. Let's look for vacancy. There's my vacancy. Let's look for self-interstitial. There's a self-interstitial. There's a self-interstitial there. There's quite a few of them around. So there. What about an impurity interstitial? So here's an impurity interstitial in a site here. Here's an impurity interstitial in a site here. What about a substitutional? So see here, this is taking the place of this lattice that atom should be there. This is also a substitutional impurity. Edge dislocation. You can see an edge dislocation right here. We can kind of start to see one forming right here. Grain boundary. You see here we have a row of atoms like this, and then it shifts just slightly here. Or you can see it here. For example, I have a row of atoms like this, and then it shifts to something that goes like this. So you have that angle, that alignment angle change. Voids, I don't see any voids here. Excellent. So I have three mystery materials, X, Y, and Z, and they are all metals, and I want to find which material is which. So we need to zoom in a little bit here. So I'm going to be a little bit, not lazy per se, but I'm going to be a little bit quick with my analysis here. So we're looking at the activation energy. So we know that we need to be looking at our Arrhenius relationship. So we know that the slope here, essentially XV is equal to exponential minus delta HF divided by KT. We're looking at the log, natural log of this. So the slope is going to be equal to minus delta HF divided by K. So let's go ahead and let's start to solve for that. So slope, rise over run. So let's go ahead and pick my initial point. Let's call at 0.02, let's say I'm like minus 70, something like that. Minus 70 in the rise. 0.002 minus the final point, so that's going to be over here 0.08. Let's say it's minus 300, so plus 300, so minus 0.008. And let's solve. The slope is equal to minus del HF divided by K, which is our K is equal to 8.617 times 10 to the minus 5. So here we go. Minus K, because we're using this as in units of basically EV per K, per Kelvin, not Boltzmann. So let's solve here. So that's 3.3. Let's solve all of them first, and then let's kind of get moving here. What about here? So same points. I'm going to keep the same times. So 0.02. Yeah, we're about like, let's just say minus 10. Again, we're not looking too closely here. Something just reasonable. Here, let's say minus 45 or plus 45. There we go. And then let's look at the last guy. So 0.02. We're at about like minus 100, 0.08, 400. So we can kind of start to see here. So we were expecting 0.5, 1.8, and 3.4. So 0.5 could be here. So the 0.5 one could be this graph. 3.3 could be this graph, but this one I think doesn't match with anyone. So again, we're looking for the analysis there rather than the final answer. So again, they're not always going to match AB is equal to C. So don't guess, show your work, and that'll be the good way to do it. All right, so let's continue. So for each material, what is the concentration of vacancies? So that was for interstitials. So if those are my concentrations, let's just take one example. So let's say we had an EV1 equals, was it 0.5? We were also saying, what was it, 3 point? Let's go ahead and look up here. EV1 is EV2 is equal to 1.8, and then EV3 is equal to 3.4. So I can do const as a function of EV and T, set this equal to exponential minus EV divided by K times T. So I could do const EV1, and I could do it at room temperature here. I could do concentration EV2, 298, and you can see the differences here. And we can also see, that's a big difference. So as you increase that activation energy, the concentration drops dramatically. As I increase temperature as well, you see I get a big increase as well. EV2, and then 1000. So you see 21 order of magnitude increases quite a bit. And then this is for self-interstitials. So we should expect vacancies to be lower, and lower by basically almost an order of magnitude. So see, you could actually have quite a bit of vacancies. So we know that based on, again, it's easier, the enthalpy of fusion is easier to form a vacancy than a self-interstitial because you don't have to push out all those atoms. All right. Frankel and Schottky defect reactions, enthalpy of formation is this. Frankel is this. Which one will be dominant? The Schottky defect will be dominant because it's lower enthalpy of formation. So let's write out all the reactions. So for my Schottky, it's going to be null goes to vacancy of BA, which is 4 plus, so that'll be minus 4 plus 2 times vacancy of oxygen. Electroneutral, great. What about my cation? BAX goes to BA interstitial, 1, 2, 3, 4, plus vacancy BA, 1, 2, 3, 4. What about for oxygen? It will be simply oxygen interstitial plus vacancy of oxygen. There we go. Now to defect reactions. So we're incorporating TiO2 into NB205. So I need to write 3 defect reactions. So one must include an anion vacancy. So I need to do vacancy of oxygen, 2 plus. Plus I'm going to do Ti replaces NB. That is going to lead me to basically NB is 5 plus, oxygen here, so there. I'm going to put a 2 in front. So now I'm electroneutral. Ti plus I need to do how many oxygens here? So I've got 2 TIs, TiO2, so I need to put a 2 in front of here. So I need a plus 4, oxygen, oxygen, X. So 2 TiO2, vacancy of oxygen. So let's see, 2 TiO2, 4 oxygens here. I've got 2 NB, and then 5 oxygens. Good to go. Let's do the next one. 205. I need to have a cation interstitial. So I need to have Ti as an interstitial. That's going to be 1, 2, 3, 4. And then let's go ahead and do plus a vacancy in NB. That's going to be a minus 5, 4. Put a 4 in front of that one. Put a 5 in front of here. So 5 here, 2 here. So 5 times 4 is 20. Again, electroneutral. And then we're going to do a 10 oxygen. 10 oxygen, oxygen, X. And that should satisfy everything there. And then finally, substitutional cation. So we'll do the same thing over here. TiO2, NB205. So TiNB, just that one dash. Plus, what else can we do here? What can we make? Let's put a Ti interstitial. 1, 2, 3, 4. I'm going to do 4 of these, so I'm going to have 5. So, actually, I think I just did that. Oh, no, I did. This is different. 5 oxygen, 4 NB, so I need 2 here, so I'm going to have 10. oxygen, oxygen, X. And that's it. So let's do the same thing for incorporation of B, basically B and Cl. So I need to incorporate BCl3 into lithium chloride. I need an anion vacancy again, so I need a vacancy in Cl. That's going to lead to a plus here. Oops. So then I'm going to do plus B replaces lithium, and that's going to be lithium is 1 plus. Here's, this actually, do I want that one? Actually, yes, I do. So lithium is initially 1 plus, 3 plus, so that's going to be 2 plus here. Plus, I'm going to do, let's do Cl interstitial minus here, and let's do 3. So I need, actually, that's it. So that'll work, because I have lithium chloride, I have BCl, and I'm clear. All right, next one. Now I need cation interstitial. So I need B as an interstitial, that's going to be 1, 2, 3, plus I could do, let's see, what defect can we do now? Because I want a negative. Let's do a vacancy in lithium. That'll be a negative. I could have done that here, but anyways, it's fun. Here, let's do 3 of these. 3 plus 3 Cl, Cl, X. And there we go. Finally, I need basically this reaction again, the substitutional cation, 1, 2, plus vacancy Li. I'm going to do that in, so I need to do, let's see here, I need how many? Vacancy in Li, so I need 2 of those. So I need 3 here, plus 3 Cl, Clx. And there we go. Now on to our burger circuit to finish it off. I'm going to choose my tangent vector here. I'm going to start here. So my start vector, I'm going to do a right-hand circuit. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. And then I did 6. So I need 1, 2. Start to finish. Those are both parallel. B is parallel to T, so that is a right-hand screw. I'm going to choose this coming out of the board here. I'm going to pick a point. Let's just start over here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Start to finish. This is out of the board. This is still in the plane, so that is B. Oops. That's oops. Uh-oh. That is B perpendicular to T. So that is going to be an edge. And then finally, over here, again, I'm going to choose this one going out of the board. I'm going to start here. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1. Start to finish. Parallel. It's also a right edge. Or excuse me, a right screw. And there we go. That's it. Congrats. Pset 3 done. I'll see you all on Pset 4. Thanks and have a good one. Bye.